maybe don't put that back up and then come down with it. There we go. Is that good? Wow. All right, today we're talking about water. We love our water. There it is. All right, good pulling water. How many of you have a water bottle with you today? All right, let's take a look at one. I'll go around and borrow. Where did you get your water? You're the best. All right. Faucet water is really good. Faucet water is tested every day. The water industry is not highly regulated, and it really ranges what you're getting. This is Poland water, Poland spring water, but it doesn't necessarily come from Poland Spring anymore. It comes from Evergreens, Clear Springs, Hollis, Maine, Evergreen Spring, Friarburg, Maine, Spruce Spring, Pierce Pond Township, Maine, Garden Spring, Poland, Maine. That's probably the original. White Cedar, but it's spring, unmodified, spring water. You know, maybe they oxidized it. I don't know. I can't tell if they oxidized it. Can't tell if they chlorinated it. Can't tell what they did with it. There's nothing said here. But at least it's spring water. Who's got another bottle of water? Here, let's do Aquafina. That's great. That Coca-Cola does that? Okay, purified drinking water. That's very different. Not spring. Okay? Not, what do they do here? Purified water originates from public water sources. F. It came out of a faucet. What's the big deal? And then purified through a rigorous 7-step purification process called hydro. Tells me nothing. This state-of-the-art process removes substances that most other bottlers leave behind. The only thing you taste in the water is water. Only. Okay, let's try this one. See what I mean? Two very different kinds of water. Okay, Nestle, Pure Life. All right, what do we learn here? Pure Life, purified water. That's good. When they say purified water, it's out of a faucet. Okay? And what do I know about the Nestle company? They used to make hot chocolate. Contains purified water, calcium, chloride, sodium bicarbonate, and magnesium sulfate. So they added some stuff to it. They purified it and then added minerals back in. So that's a little different, okay? Who's got another bottle? Anybody up here? You got two out of a faucet. Laura? That's great. Out of a faucet, fantastic. Anybody got commercial water? Here, out of a faucet, okay? And so you read carefully. You know, I bring in faucet water every day. Let me see that one up there. I see a different one. Okay, smart water. The lights show smart water. You know, there's nothing published here that's useful. Nutrition facts. Calories, 0. Hey, I think I know this. Total fat, 0. Sodium, 0. That's the one thing good they told me. No sodium. Okay, why is it 0? Total carbonate, 0. This is nothing in it. It's 100% water. I was looking for my little water meter. I have one. But I couldn't find it. We go around and test your waters. We'll find out what your faucet water is like. All right. Where do we get this water from? We got a lot of words here. Nutrition size.
It's inside the bottle. The writing inside the bottle.
Glacial smart water. Yeah, vapor. Oh, vapor distilled. They distilled it. It's not from a glacier at all. It's distilled water. It's from a faucet. And then they added electrolytes, chemicals, for taste. Crazy. So, buy smartly. It's really different than spring water, faucet water, purified. A lot of it's been modified, all right? So water's great. And, you know, I've talked to you many times about what you could do. 4 years at Boston University, walk out the doors, and would you have a job? Water. The demands for water, clean water, are never going to go away. All right, and there's so many of us now. All right? And a lot of our water is not available. Most of the water in the world is where? In the oceans. Yeah, and of course the Middle East countries, they got the money, are thinking about purifying seawater. Well, once they do that, what are they going to do with all that salt? All right, so it's very expensive. And then the next great source of water is ice. They get the ice caps. So you're going to have to tow an iceberg. Well, they've thought about doing that in the Middle East too. It's kind of wild. And then you think, oh, well, lakes and streams, look at the Charles River. Actually, there's very little water in lakes and streams. Lakes more. Most of the world's water is underground. It's called groundwater. And it's everywhere. Down there. All right? In nature's own way, it gets purified. Bacteria break down things over time. The sediments gradually filter out what's there over time. It's down there for 280 years on average. The average life in water in a river is like 12 days. It rains and it flows, finally gets to the ocean. But for the water in the ground, it's over 280, I think. We'll see the numbers in a minute. So it's down there for a long time. It moves very slowly through the ground. There's a source area where it rains, like up in the mountains, and through gravity, it moves down. When water comes out of the sky, part of the hydrologic cycle, we've talked about the hydrologic cycle because it makes rivers. But it starts out as rain. Rain, some of that rainwater does flow into lakes and streams. But the earth is porous in the upper portions of it. The earth's upper sphere, the crust of the earth, is porous. It's cracked. It's made out of sediment or something like that. And so a lot of that rainwater, I'm falling down through the rocks. And it sinks into the ground. Now, deeper inside the earth, in the deeper crust, under pressure, those cracks close up. And so the earth's crust is like a bucket. And the upper part, water flows in, but there's a bottom in the crust where it gets higher pressure, about 10,000 feet down. It closes up. And so water's down there, all over the world. Okay? If in drier areas, it's not very abundant. It's really deep, hard to get to. In some areas, it's salty. In some areas, it's contaminated by natural oil. All right? So it's not always good, but it's down there. Down there. And it's a lifeblood for lakes and streams. If a lake is not touching the groundwater table, so down it goes down, and the top of that water surface under the ground is called the groundwater table. Where the groundwater table comes to the surface of the earth, it makes a lake or a stream. But if we drill and suck that water where it starts dropping the groundwater table, what's going to happen to the lake and stream? It's going to dry up. And the trees are putting roots down to the groundwater table. What's going to happen to them? Because you sucked it out. They're going to die. All right? So these are some of the issues, good and bad. Easily contaminated. You spill a can of gasoline out on the ground because you were trying to fill a lawnmower. Where's that going to go? To the groundwater table. Yeah. All right, so let's go take a look. I love my clicker, Mama. Somewhere, over there. Groundwater resources and pollution. So there it is. Most of the water is salty. Where is it at? Well, 97% is in the oceans. Can't drink that. The next bit abundant is ice. That's kind of hard to do. Lakes and rivers are really small. So it's groundwater is a distant third, but it's number 3. Okay? And it's down there. Okay, the jobs for you. All right, there it is. Fresh water on Earth, mostly out of the ground. The oceans are salty. You can't drink ice. So fresh water, where we find it, mostly out of the ground. Whoa, look at these guys. And a place for all of us to feed. They can't do anything about that water quality. You can. Hey, guys. Woo. Okay, come on back. Come on back. Come here, it's okay. Okay, good. Oh, they're thirsty. Bye. So, it is part of the hydrologic cycle. Since 97% of the world's water is in the oceans, then 97% of every raindrop comes from the oceans. Right? Part of the hydrologic cycle, we're evaporating. That's the beginning. And since most of the world's water, 97% is in the oceans, that raindrop, why doesn't that raindrop come down salty if it's 97% from seawater? That's a good. Samantha? Charlotte? Yeah. Salt does not evaporate. Salt does not evaporate. You know, one thing I don't see in the water coming, why isn't somebody catching rain and selling rainwater? Comes down pure. All right? Maybe you go out and do that. Go to Seattle, catch rainwater, sell it. No one's doing that? I don't think so. All right? And so it's all part of the hydrologic cycle. Then it precipitates on raining and snowing. Some of it runs down the streams. Doesn't live long. But most of it sinks into the ground, where it takes a very different, very slow journey, helping trees and grasses and flowers grow, keeping lakes living and rivers flowing. It's there, all right? So where we precipitate, it infiltrates into the ground, and then there's a bottom. And that can be a bottom layer that's tight. We call it aquiclude or aquitard, and you'll see both names. And I'm sorry that there are both. It's like exclude. It excludes the water because it's too tight, or it's a layer like shale, like mud. Water can't get through it. So whatever that is, that confining zone, the water can't go through it. It fills up like a bucket, all right? Here's the top of the fill zone. So that's the groundwater table, a little higher underneath hills, a little lower in low spots, but where it touches the surface, it makes streams and lakes, all right? And trees will project down and find that groundwater table, put it down really deep, 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 deep roots, all right? Okay? So water underneath the ground is simply in water-soaked rock. Water down in the ground is not down there as lakes and streams. There is no such thing as an underground lake or stream, with the exceptions of sometimes in caverns. It's down there in water-soaked rock. Okay? And you drill down into that, you're into that rock, and you start sucking it out slowly, because it's not going to move easily. Okay? And that's what it's there. That's what it's down in here. Here in the zone of saturation, it's in between the grains of the rock or in the cracks in the rock. All right? And depending on how porous the rock is and how permeable those connections are, that water moves very, very slowly. A sandstone is a great rock. We call that an aquifer. A rock that contains a lot of water. And the water is in between the grains of sand. Other rocks are cracked. They're fractured, so they're in the fractures. That's okay too. A fractured granite will work out well. Now, a granite that's not fractured will have nothing. A shale that is not fractured will have nothing. There, the water can't move. Okay, so porosity refers to the open space, and the permeability is how well it's connected. How well will the water flow? So groundwater, like a glacier, is always moving downhill. Downhill. It accumulates up in the mountains. Accumulates up in the mountains. There we go. And then is always moving down, down, downhill. All right? There it goes. And then when we start sucking it out, we actually get what's called a cone of depression, where the water table suddenly gets sucked away. That's called a cone of depression. And you find out you got to drill deeper. All right? Water moving down into the well. So, rate of exchange. How old is that water? This is about the numbers I was trying to remember. 11 days. I said 12. That's how, on average, that's how long water lasts in a river before it hits a lake or an ocean. Okay? In contrast, groundwater's down there for a long time. I guess 200 something. 280 years is an average. Some of it's a lot longer. All right, some of it's shorter. That's just the average. The groundwater flow, inches per day. So if you come in and you suck out gallons per minute, the groundwater table is going to be harmed. And down it goes, okay? So porosity and permeability, oh, we love water down there. Water flows. Where it comes to the surface, it makes a spring. Springs can flow all year round, even in deserts when it doesn't rain for most of the year. Why is that? Why would a spring flow all year round in deserts when it hasn't rained? Because the water moves really slow. It's called Darcy's Law. Water moves really slow. And I want to demonstrate that for you. I need a garbage can. Can one of you guys go get me a garbage can? Yeah, thank you, Ellie. I need a garbage can, but do hurry, because I'm about to demonstrate something here. So I brought some sand. Find a garbage can. Otherwise, I'm going to have a mud bath. And come here. Come here and hold that for me. You're good, right there. Thank you. Pour in the sand. Hold up. Uh-oh! I got a leak. Wait. Hold that back. Let's start over. Like that tire we had. All right. Bad being supposed to be. Try it again. Oh, all right, got it. Good. Excellent. Stop right there. Now, so that's my rock of sand, okay? That's the rock of sand. And, could you come up here? All right. You can help me as well. There we go. And I guess I could just go in this bag. All right. It means a holder of rock. It's got to be where you can see you. Oh, here's a garbage can. Okay, great. All right, we don't need to go in the back anymore. I'm going to demonstrate Darcy's law that explains that water moves really slowly through the interstices. There's a lot of friction. All right. And so let's say we live in the desert, not Boston, and it rains only part of the year. So it rains in the wintertime. So it starts raining in November and December and January and February. That's pretty good. And you know, and then the rains in March, they finally stop. And you are going to go, aren't you? It moves really slow. There. Listen. Hold it up higher. Really high. Excellent. How many of you got the pee right now? Look at that. And so it's April and May and June and July and August and September and October. The spring is still flowing. The spring is flowing. Then we go into a drought. It doesn't rain in November or December or January, February or March. But the spring is still flowing. It goes into the next year, into April and May and June and July. The spring is still flowing. It's still flowing. You see what I mean? It flows really slowly. All right? So it's down there. You can set that down inside. Thank you. Excellent. Excellent. All right, so that's a bit about Darcy's law. We'll see that. Porosity does vary depending on the kind of material, whether it's fractures or in between the grains. Darcy's law. All right, you start with a cross-sectional area. You have a flux that goes through slowly over time. You do not have to remember that equation, but I want you to know that it's explained by something called Darcy's law. Streams are fed by the groundwater table. They feed it, okay, through their springs. But once we come in and drop that groundwater table, this is called a losing stream. It's dying. It's dying. It's going to simply go away, all right, during a drought or because you did it. It comes down. The stream appears to evaporate. It didn't evaporate at all. It sunk away. All right, it's no longer connected to the groundwater table. Here's an example. Look at the Mojave River out in the Mojave Desert where we just were, coming out of the San Bernardino Mountains and disappeared. Where did it go? Is it correct to say that it dried up? No. The groundwater table is no longer at the surface. And it sinks away. It sinks away, all right? So wherever you see surface water, that's where the groundwater table is. Look around. Look at the lakes and streams. The Charles River projected underneath BU, and that's the groundwater table. That's how far we'd have to dig to find water. All right? Here we're looking at a Yucatan well in Mexico. Oh, let's go. A site of religious activities for many centuries. But where's the groundwater table? You're looking at it. Okay? So go back over here, drill down to that same depth, and you'll reach water. Will you reach standing water? No. Water-soaked rock. Okay, water-soaked rock. Here we are in Butte, Montana, a copper mine. One of the biggest at the time. Where's the groundwater table? You're looking at it. All right? So back over here, and I'd have to drill down to that depth. Are you going to hit standing water? No. You're going to hit water-soaked rock. It moves really slowly. All right? Groundwater is down there, and it does change with depth. As you go down, it gets harder. Deeper water has been down there longer. It's older. It's hotter because as you go down inside the earth gets hotter, right, when we go down? And hotter water dissolves more minerals. So it's harder. So the deep water you really don't want. It's not as much there because the porosity is tightening up. Okay? All right? It's an industry. You want a job. Water. Water. Feed the world. Water. So it's harder, hotter, older, and less abundant. Okay, as you go down, down, down. Water purity. The standards aren't great. We have trouble getting good laws passed because the industry's powerful. And you're not being told much about your water, but so we did learn, you now know the difference between, is it spring water or is it just modified faucet water? And they say purified drinking, guess what? Couldn't take it out of a faucet. And then the dissolved solids need a limit. Your body likes a little bit of calcium, a little bit of sodium, but the element varies. The maximum of that element varies. Okay, so the total dissolved solids, the maximum allowed is 500 parts per million for total dissolved. We don't see these numbers on most of these bottles. We saw a 0 for sodium on one. For a lot of times they're not telling us. Calcium, the absolute limit is 180 parts per million. Sodium, the maximum limit is 70. What does sodium do to you if you get too much? You bloat up. You bloat up, all right? Yeah, you start getting hard. It causes your body. The metals and non-metals screw around your body. You need a little bit, all right? And then as you get to the really heavies, the limits are even lower. Barium, body can't take much barium. They put barium in you to make x-rays. Barium makes your stomach go poo-poo. Right away. 1 ppm of copper, liver damage, iron, and you can taste it even when it's small. Lead and mercury attacks your nervous system. Your kidneys will fail. It will kill you. All right? And you don't know what's in that water. We're talking about very small amounts of these kinds of metals. So, in general, total dissolved solids, anything less than 60 we call soft, 60 to 120 we call medium, and then hard water greater than 180. Okay? Oh, lovely water. It all depends where it's from. And next year for this class, I'm going to go out and analyze the Charles River, and I'll talk about local rivers here so you can see it and apply it for what's around. But we do things. Now, a lot of places will use deionized water, or they'll use ion exchange columns. And a water softener is usually an ion exchange column, where they're getting rid of one element and putting in another for it. So it's not really getting cleaner. Usually what they're doing is getting rid of calcium and magnesium, which are divalent cations. They are 2+ cations with twice as many sodiums because they're 1+. So it's a 2-for-1 exchange. They take out one magnesium, they'll put in 2 sodiums. Is that what you want? And it makes the water seem to be soft. So soft you can't get the soap off. Have you ever had that experience? It's sodium. And it causes you to bloat. So think about that. So it's all there. Springs are where water, groundwater, sometimes they're on faults. Groundwater comes to the surface. If it comes out under pressure, we call it artesian springs. So there's the groundwater table. Here is a fault. You can see the fault. And look at the water come out. Faults are a barrier to the groundwater flow. They're coming underground from the mountains. They can't get across the fault. And so they bubble up to the surface. Faults often have springs all along them. Or early settlers would find the springs, follow the fault line. There it is. And then it's a surface stream where it bubbles out. Wow, light. Water under the ground can't get across the fault because the fault has ground rocks into being clay. Clay is impermeable. We can make a mud pot that holds water out of clay. It's impermeable. So water can't get across. Here's another one with a volcano for scale. Holy God. You look at all the vegetation on that side, so that's where the water is bubbling out here and then on the surface flowing out that direction. Okay? Sometimes the water table is perched. This is near Idaho Springs, Idaho. The groundwater should be down here. Here's a stream, but there's springs coming out above that. How'd that happen? Well, this is a perched aquifer. There's a layer up here that is an aquitard or aquiclude, and water coming down. Can't get down to the stream, it bubbles out above it. Look at that water coming. Look at the spring. When it comes out under pressure, that's called artesian, and that requires special geologic conditions that the water is geopressurized. It's gone too deep. It wants to come up to the surface. It's trapped down there, and it works. Look, there it is. Artesian spring. Let's go jump in. Oh yeah, and sometimes it's warm because it's been very deep. It might be a hot spring. Love that. We can make an artificial artesian system for our homes by having a water tower. We pump the water up into the tower. It sits up really high. That gives it pressure. So when you're down here and you turn on a faucet, it wants to shoot up to that level, which gently declines away from the water tower. But it's there. So that's why we put water towers. So your homes have pressure. Where in communities that don't have water towers, they got to use electricity and pumps to give you that water pressure. But here we just use gravity. Okay? There it is. There it is. And this happens in nature as well. They'll drill down and hit it. The water goes down. It's caught. It's confined by an aquiclude above and below. The water table wants to be right there. And it can't get there. And so it is, if you drill down into it or it hits a fault, then it'll erupt and try to get to that surface just like in the water tower. So those are artesian springs and wells. Look out! Whoa! They hit it! There it is! Water under pressure! Drilling down! Hit the groundwater table. It was confined. It wanted to be up high. And there we go. Now, water does something else. It dissolves, because rain is naturally acidic. It dissolves limestone and marble, the mineral calcite. It dissolves. Calcite dissolves because rain, again, is naturally acidic. And so here we're at Carlsbad Caverns, New Mexico, but caverns are everywhere, that there is limestone. And this is a special kind of erosion that happens with groundwater very slowly. Let's go inside. Woo, woo, woo. What are those? Oh, yeah, bats. Bats. Wee, 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 wee. They fly around. How do they see? How do bats see? They don't. They have radar. They get confused by hair. They get caught. And they have teeth and claws. They're putting out sounds all the time you can't quite hear. They make little squeaky noises, but they hear it sonar. All right? Sleeping, nodding, nostril. How could you sleep with me shouting? I see everything. All right, there we go. Wee, wee, wee. And so as the cave is formed by dissolving away, and it's underwater. So there's a case where we have standing water. So the cave is formed underneath the groundwater table, and it's filled with water. After uplift, the cave then gets lifted out of the groundwater table, and it still has, now it's a cave. So it takes uplift to get the cave out of the water table. Active farming caves are below. Uplift the land, Colorado Plateau, lifting up, and now it's out of the water. Water is still dripping through it because water is going down. So as the water goes down through the cave, wanting to get to the groundwater table, it starts precipitating in the cave, precipitating calcite, the mineral, making these columns. Coming down from the top, they're called stalactites. Growing on the bottom, it's called a
Stalagmite?
Stalagmite, thank you, Ellie. Stalagmite. Calcium carbonate dripstones. Beautiful. Forming, coming from the stalagmite, stalactite coming down. Sometimes it's an entire column. So the water is drip, 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 dripping, just like we heard, dripping through. And as the drop comes down, a little bit of it evaporates, leaving behind. So we dissolve the cave, and now we're reversing the process. We're filling it in. All right? Filling it in with columns of dripstone of various kinds. And so here, oh, they're just kissing. Kiss, kiss, kiss. So what mineral is forming here? Calcium carbonate, the mineral is calcite. Calcite, the mineral of limestone and marble. All right? Dripping down, making, look at the new crystals go. So if I show you that on Thursday, multiple choice, what mineral do you choose? Calcite. All right, there you go. Gift to me. So here is the cave It once formed, now it's filling back in, but with dripstones, giving back to nature what was once taken away. Then, as that cave gets near the surface, here's the caves actively formed.